Welcome to this little summary, this little talk about everything I've learned at my university studies. And I studied electrical engineering. It's a fascinating subject. I got a lot of fascinating subjects to cover that I studied in 10 years. 10 years. And when I started making this document, I thought it would be impossible to make, but I think I got the grasp of everything that encapsulates all of it because electrical engineering is such a broad uh, curriculum. Like, you got nuclear engineering, you got scientists, you got mathematician, you got biologist, you got chemist, you got mechanical engineer. And then, like, if you go into mechanical, you have aerospace engineering. You have civil engineering, structural engineering, mining engineering, mineral engineering. Um, but within electrical, there's so many different topics that require a lot of knowledge and research, which is what we're going to go into. But a little bit of background about the other engineering and science fields. They're very fascinating too. Science is a very complex, high-tech, fascinating, and rewarding field to participate in. People think it's just about designing something and following a budget and talking to project managers and working with the client and following laws and creating a design plan, creating alternative solutions and building something. At the very end, that's what it is. But the core fundamental physics phenomenon and natural science and mathematics and just principles and laws that we've discovered over hundreds and thousands of years go into all of the research behind technology and these designs. So without further ado, that's a little bit of background about the other engineering, because I can't say any more about them because I never studied them, so I don't know what I would be missing. But they're very fascinating too. Like, you got the fundamental laws of chemistry, the heat laws, and for civil and structural engineering, you got the force laws of gravity, how well a structure can stand. For cars, you have, and airplanes, you have buoyancy, how well it floats, how fast it travels, the acceleration. And for electrical engineering, they say it's V equals IR. Voltage and current and resistance are related. So, but let's get into it. So, I don't know how long this video is going to be. This video is going to be... It's fascinating, though. It's fascinating. And it's everything I learned over the past 10 years. And you can also look for lectures or videos on the topics I'm going to list. So let's get into it. The first thing we have is electromagnetism, fields and waves. So what is that? Basically, it's charge. You know what charge is? When you have two charges, they can either repel each other or attract each other. And there's positive charge, a proton, and a negative charge, an electron. So when the clouds get stormy, the clouds get a whole bunch of negative ions, negative charges. But they can't travel to the ground as lightning because there's no conductor. Air is not a conductor. So it needs to travel down a wire, a conductor. A conductor is something that has allow a lot of electrons to travel through it. And the ground, it turn when you have all this negative charge, it's so powerful that it's causing the negative charges to repel each other on the ground. So the ground starts becoming more positive because of this negative charge. And the force sometimes becomes so powerful between the two that you get a breakdown in the air. And then a path for a split second actually does allow electrons to travel and discharge into the ground. And that's that huge, powerful lightning, which can go into billions of volts. So when you have charges, they attract and repel each other. Same with magnetism. You have North Pole and South Pole, and North Poles attract South Poles, North Poles repel North Poles. And the Earth is a magnet, and the sky is a charge, and the Earth itself is a ground. Now, when we design circuits, the fundamental rule is there's no possibility for electricity to flow without having a loop. So you need to have a closed circuit, and then electricity continuously flows within that circuit until it runs out of power or until the circuit is broken, a switch is flipped off. That's why switches exist, because switches just change it from a circuit to an open circuit, and if it's not closed, no electricity can flow. The one exception is if you're connecting to ground. That's how lightning flows. Because the ground is so big, it counts as an infinite circuit. It just goes in the ground forever and ever and ever and ever and ever. So anytime you connect to ground, when you plug something into your house, an appliance like a washing machine or a refrigerator, it'll go into ground to be safe. So that's fundamentally what electricity is, electrons and protons. And protons usually don't do much. Protons stay where they are, and electrons are the ones that travel at the speed of light. Nothing travels faster than the speed of light. The only thing that equals the speed of light are electrons and other subatomic particles, mainly electrons. And when you get them to, the thing about electricity and magnetism is they're related. When you see a ray of light, it travels as a wave. Okay? Like a wave. Now what's special about it is a wave needs to travel in water. Or it needs to travel like an earthquake across the land. Or it needs to travel across the sand. It can't travel in space. But light is very special because it can travel through space to infinity. Why? Because it's an electromagnetic wave. So it's got electricity, electric field, and a magnetic field going like this in circles. One is this way, one is this way. And they rotate in circles. That's called the polarization. And so electromagnetic wave is, there's a wavelength and a frequency. Frequency is related to wavelength. So when you get ultra short or ultra long waves are like radio waves. They can't penetrate through buildings, so they have to be built really high up, high towers, because they can't penetrate anything. Gamma rays, UV rays, are very short wavelengths, like a millimeter big, or nanometers big. And they can penetrate your skin and cause cancer. So gamma rays, X-rays, UV rays, they all vary in their wavelengths, all the way up to radio waves. And somewhere in the middle is the wavelength of visible light. And they also vary. That's why you see colors. Blue, red, green, yellow, all are separated by differences in wavelength. That's the visible spectrum of light. They're wavelengths, and it's literally a wavelength. It's like one wave is between, For light, I think it's like a meter or something like that, or half a meter. And for radio waves, it can be 100 meters. And for UV rays, it can be a centimeter. And that changes how much energy it has and what it can penetrate. And the two more things I'm going to say about fields and waves. This is the core fundamentals of electricity. You got electricity, charge, you got magnetism, you got fields and waves. Then you have the mathematics. So you have integration, derivatives, and then you have these transforms. So transforms are because a lot of times we use imaginary numbers. Imaginary number just means the square root of -1. Nothing. -1 times -1 equals 1. You can't multiply two numbers and get -1. So the square root of -1 doesn't exist. That's why it's the only imaginary number. And we use that a lot because we have when you graph them, it's called the real imaginary plane. So you can have a real number, half and half. A real number mixed with an imaginary number. And that creates like real power and real impedance versus reactive power, phantom voltage, phantom electricity. Things that aren't real, but that need to be calculated and have an effect on, such as the phase. And if you don't take that into consideration, your calculations are going to be totally off. You need to take imaginary. So imaginary power has real implications on real design and real voltages. And the way we calculate integrals, derivatives, and trigonometry. Why trigonometry? Not because of a triangle, but because we said it's waves. Everything is waves. And what is wave? A wave is a sinusoid. And you got two sinusoids. You got sine and cos. And they're the exact same thing, just inverted. So you have one wave, sinusoidal waves. That's also called alternating current, AC, because sometimes it's up, sometimes it's down. It's alternating. So that's where trigonometry comes in. So when you have mathematics like imaginary numbers, derivatives, integration, differential equations, derivatives, and then trigonometry and sinusoids, it's very hard to calculate all of that. So we got these two transforms, the Laplace transform and the Fourier transform. And we just transform that. It's very complicated, but we have tables. We use tables. We don't do the math ourselves by paper because it's very mathematical complicated. But we have a table. So when you have our real life number, we transform it with a table into the frequency domain, where it's all imaginary. And then it's a lot easier and simpler to calculate. Very simple to calculate. You just have a J, W, or an S. Angular frequency. That's it. And then to convert that back into seconds and time, real time, and real waves, we just use our table and convert it back into. So that's the mathematics, the electricity and the magnetism, the waves, the sinusoids, the trigonometry, the Laplace transform, the Fourier transform, the real and imaginary numbers, and that is the fundamental, and the circuits, open circuit, closed circuit, and that is the fundamental foundation of the physics behind all electrical engineering. That's the fundamental physics. Everything else can be built off of that to an extent. exciting. So using that, let's just explain now the different topics that incorporate that stuff. The first very exciting thing is the nature of light. We still don't know what light is. Is it a wave? Because a long time ago, a physicist came up with the idea that maybe it's not a wave, maybe it's a particle. And how did he figure that out? He said, okay, if it's a wave, right? That means if you can find one photon, one individual quantity packet of light, and shoot it at a detector, you should see a wave pattern. So if you have light in a dark room and you shine it against a detector, one photon at a time. After you fire maybe 1,000 of them, it should look like a wave. But that didn't even happen. He found out if you fire one photon at a screen, all the photons fire like a gun and hit the same point. That looks like a particle, because a particle goes in a straight line. So the light wasn't behaving as a wave. But if you fire all the photons at once, then light behaves like a wave, and it looks like a wave. So what happened here? How is it possible that when you shoot one at a time, all of them hit the same spot, and when you fire them all at once, they go like a wave? The truth is, light is doing both things, because it's called the double slit experiment. He cut 2 slits into a screen, and he said, this will solve the mystery. We're going to shoot one particle, and it's got to choose which hole it's going to go into, which slit, and where it's going to line up on the screen. So it's either got to be a particle or it's got to be a wave. One photon, but it's got 2 options. So it's got to decide for itself whether it's a particle or a wave. And when they shot one photon, they thought it was going to be like a particle because it's just one at a time. But when they did the 2 slits and with one photon at a time, the photon now behaved like a wave even though it was just one particle. So one particle was interfering, performing constructive interference. How do you have interference? When you have 2 things like a wave, 2 waves going at each other, and they crash, they make an even bigger wave. But that's not possible when you have just one particle. But that's what happened. So there was one particle that ended up interfering with itself and creating a bigger wave. Yet it was still one particle. So light, we still believe it's a particle and a wave at the same time. And there's a very interesting mathematical equation called the wave equation. It's very complex. You have a partial differential equation, an ordinary differential equation, and you have the Laplace transform all in one. And you have a wave equation. This leads into quantum mechanics, another area of investigation. Quantum mechanics means you can either know where the particle is or which way it's going, or its speed, like that. You can't know both. You can't know everything about a particle. You either know where it is or where it's going, its path. You can't know both at the same time. Quantum mechanics is very mysterious. But it's at a very tiny scale, electrons and photons. That's why my research was proposing, how can we solve the interaction between electrons and photons, and can we communicate with light, like fiber optics or solar power, light turning to electricity? How can we optimize that? And is there any new discoveries we can find out with photons interacting with electrons? Because both are quantum, Both are traveling like speeding bullets. One is a wave, one is a particle, one is a charge, wave, particle, frequency, energy, wavelength, voltage, and current. So that's very interesting, whether light is a wave or a particle. It's both. And then you have things like refraction. So when light, why can't we grab a fish from the water? Because when light hits water, it bends. So light can travel through space till infinity, but when it hits water, it bends. Water can bend light. So the fish looks like it's over here, but in real life, it's over here. And that's how glasses work as well. You have an object, it gets bigger. You have an object behind a screen, it's actually not there. You also have imaginary objects that are placed behind screens that our eyes can't detect. And sometimes light can bend so far that it bends greater than 90 degrees. And that's why you have a fiber optic cable. A fiber optic cable is light that's bouncing off the cable at such angles that it can't escape. That's called total internal reflection or total internal refraction. So that was the first area, the particles of light. And there's such Einstein's theory of relativity. We'll go into this too. This is going to be a long video, but it's very fascinating. Einstein proposed an experiment that actually turned out to be true, which is not shocking. But he said you can slow down time. And time does slow down, depending on your speed. Why is this true? This is the experiment. If you were to have a rocket ship traveling like this, and you put a laser on the rocket ship, and the laser had to shoot up, bounce off of a mirror, and come back into the detector. What's the speed of the laser? The speed of the laser is the speed of light. 3 times 10 to the power of 8 meters a second. So the rocket ship is going nowhere near the speed of light. So the rocket ship goes like this, and the laser goes like this. Bounce, bounce. But if the rocket ship could somehow travel close to the speed of light, then the rocket ship would be traveling like this, but the laser would be traveling like this. So the laser would be looking like this. Because by the time the laser goes up and comes back, the rocket ship has moved. So to someone standing on Earth looking at the rocket ship, they see the laser traveling like a triangle because the rocket is traveling so fast. But to someone on the rocket ship, the laser travels up and down. So the rocket ship sees the laser up and down. So it's aging at the way it's supposed to age. But people on planet Earth see it aging slower because the light goes like that. So time, and what happens when time has to travel like this and like this? It has to travel a much larger distance. So because of that, it's not the same anymore. One's like this and one's a triangle. The two times are different. So, and this is true because if you're on a plane for your whole life, you will biologically age slower than people who are standing on the earth for their whole lives. It's not true. You're both aging the same. But the universe works that it's relative. So the people on earth see you aging slower. And the people on the rocket ship see the people on Earth aging faster because of the same fact that nothing can go faster than the speed of light. But if something carries something close to the speed of light, then time gets dilated, and space and distance are related to time because time is meters a second. Meters, second. Meters is distance. So velocity is meters a second. It's traveling. So velocity is meters a second. So distance and time can be changed relative to who's standing where. This is true because when we observe things from space, they don't follow the natural laws. They follow this relativity laws. We see particles and quantum particles that reach our planet that have a lifespan, making it impossible to ever come close to our planet. But they reach our planet because they're aging slower and living longer than us. So we can detect them on our planet. It's very true. Google it. Wonderful, fascinating. Whew, it's a lot of stuff. Let's see. Let's go into something softer, lighter topic now. Lighter topic, probability. Now, what's probability? There's 6 sides on a dice. So there's a 1 in 6 probability you're going to hit your roll. There's 2 sides to a coin. There's 50% chance you're going to guess the coin correctly. But there are theories and theorems that say we have this coin, right? If we were to flip it 10 times, what are the chances that 3 heads come up? Well, that's 30% probably. But what if we were to flip it 10 times and repeat that 5 times? How many times would we get 3 heads to come up? So you flip a coin 10 times, and that's one trial. And you take 5 trials. And in 5 trials, how close can we get to 3 heads? What about 1 head? 1 tails? How many trials? If we take 50 trials, what are the chances we get 1 tails? And the most complicated is, say we take 1,000 trials. What is the probability? Yeah, that was it. What was the probability that 70% of the time we get tails? Or how many trials do we have to take flipping a coin to ensure that 99% of the time, 99% probability that we will get tails 70% of the time? So we want to flip a coin 10 times. And in those 10 times, we want tails to come up 70% of the time. How many trials do we have to take to ensure that at least 1 trial we're going to get tails 70% of the time, but we want to take enough trials to guarantee that we are 99% accurate? I had that as a question on my goddamn probability test. That's why I did so bad in that class. The probability of how many trials you're going to flip a coin 10 times to be 90% accurate that tails is going to come up 70% of the time. But we can calculate that. Very complex, but we can calculate that. Then we have electric machines, so electric motors and generators. Electric machine is using electricity and magnetism at the same time. So when you have a magnet and an electric field, they're related. Electric field, this is a very fascinating phenomenon. An electric field can create a magnetic field. And the magnetic field can create an electric field. And what is an electric field? It's a current. So current creates a magnetic field, and current and a magnetic field can create a force. So we can get force, magnet field, and current, electric field, all related. How fascinating. That's how generators work. That's how motors work. How exactly? You need a loop of wire, but there's no current in it. You take a magnetic field and you start radiating it through the wire. But if you just put the magnetic field through the wire, nothing will happen. It's how fast you change that magnetic field. So the magnetic field, that's where the rotation comes in. You need to rotate the angle of the magnetic field, or the strength of the magnetic field. And how fast you can rotate it will result in how much current you're going to get through that wire. And the minute you stop rotating, current stops. So that's how a generator is ran. It's just spinning. You need something to spin because you need to continuously rotate the angle. So you use steam, you use coal. Why is coal bad? Coal generators are used to create steam. You burn the coal, you create pressurized steam. Pressurized steam spins the generator, spins the magnetic field, spins the turbine. Turbine creates a magnetic field that goes into the coils that creates electricity that then gets distributed across entire cities. So it's all about finding ways to spin this turbine. Water, nuclear, splitting atoms to heat water to create steam. Natural gas. So that's fascinating as well. And now we'll get into more technical stuff. That was mainly the fundamentals. Let's get into some technical stuff. So we got electric machines, we got generators, we got fundamental electricity, magnetism, and force. We got wave theories of light. I'm going to talk a bit quieter because this is killing my throat. Okay, so let's talk about control systems. Control systems control a system. What does that mean? You have one factor you'd like to control. Say you have a car. You can control speed, acceleration, position. Okay, that's not hard to do. If you want to control the speed, change the gas pedal. That's not hard at all. The hard part is when you have external factors. What if the road becomes slippery? What if you hit a bump? What if you go up a hill? What if you go up a hill and then down a hill, then up a hill, and then turn, and then slip, and then you need to brake from another car, and then you got to accelerate again to not get hit from behind? You need a control system, which is going to take the speed you're going at, take your external factor, mix them both up, and loop it up to continuously regulate. So it's about regulating. And you have different types. You have ones that are going to regulate it so fast that it's going to be like this. The problem is it's going to overshoot. So it's going to, if you're down, you're going to go up, but you're going to shoot up. And then you're going to shoot down, and then you shoot up. So you're going to go like this by the time. So you're going to overshoot. Then there's ones that'll take a long time to regulate, but they're not going to overshoot. So it's going to look like this. So that's a control system. You can control voltage, current, speed, force, anything. You can create a computer, or it doesn't have to be a computer. The first engines had control systems. It would be like a weight, and the weight would spin. So when the car was going too fast, the weight connected to a rope would spin fast and make it heavier for the car, and the car would slow down. That was the old steam engines. That's a control system. Fascinating. The next thing is you have amplifiers. So transistors. Transistors take 3 inputs and produce 1 output. What does that do is when you have current, voltage within a small circuit, we can copy these circuits. And what's the first thing that happens when you can manipulate something in a communication network? You have control now. So we can amplify, we can copy, we can invert, we can talk within our circuit. We can change the voltages. So if something needs this much power, we can provide it that much power. This needs that much power. Voltages and currents talk to each other. Sometimes an encrypted message. An encrypted message means it's this much power versus that much power. So reading the message, something like that. Because your phone and your computer is thousands of billions of transistors. Little switches that talk to each other by just changing voltage and current. And that's how you can encrypt a signal before you radio it out into an antenna and then receive the signal, decode it, amplify it into a speaker so we can hear it. So when you send it out, it uses little power. And when you receive it, it takes big power to read the message. And finally, the last topic. Interesting, but last. How a computer works, software and hardware. Computers are 3 things. You have a central processing unit. All it is a clock, just a clock. Gigahertz, how fast your CPU is. And the CPU executes 1 byte, 1 bit at a time, every time the clock ticks. So the clock ticks, 1 byte moves. What happens to these bytes? They get sent to registers. Registers store bytes. They can be small, bigger, and bigger. And each register You store information, then you read it into the CPU, and it executes another register. So registers store information and commands. So you get a command: change this, execute that, load this, read this, write that, change this byte, change this bit. And when you have a screen, like a screen, or an input like a keyboard and a mouse, those are used as bytes. Those are read as bytes. And each pixel is a byte. Turn it this color, turn it that color, turn it that color. Move the mouse to this pixel. Type this key with this pixel, with this byte. But you can program a machine that doesn't have a CPU. You think a vending machine has a CPU? You have wires, and literally, you pressing a button turns on a series of wires that have an on voltage or an off voltage. So you press a button, you input money, you get change. It calculates the change. It calculates your selection. It dispenses your selection based on the button, what it's wired to. And they're wired with gates. So 4 wires go in, 1 wire comes out. That wire goes into another gate with another wire. And at the end, you get 1 wire. And that 1 wire tells you a certain byte. And when you add up all these wires together, you can get a bigger number with different bytes. And when you get a lot of bytes together, you can get a bigger information, like how much change should be returned. You can create more complicated things than vending machines with just, that's called hardware. Verilog assembly is just wires and logic gates. Now, you can create robots like that. No CPU, no clock, no executing commands, no registers. But then we have software. Software is higher level. So instead of doing the wiring yourself, you tell the software in human language what the wires are supposed to do, and they do it themselves. And that's that. That's that, ladies and gentlemen. Those are the fundamental technical areas of electrical engineering. Interesting. Very exciting. You can Google more lectures and YouTube tutorials and stuff like that and learn about it the way I mastered it. Okay, stay intelligent, learn, research, and grow.